In Chapter 10, Section 3, we're going to start looking at gas laws. And the gas laws are the laws that describe how ideal behaving gases will behave. So what makes something an ideal gas and how does it behave? The first gas law, chronologically, the first one that was derived, came from Robert Boyle. And what Boyle told us, and you'll see when he did this, 1660, that was a long, long time ago. What Boyle told us is that the volume of a sample of gas at a given temperature varies inversely with the applied pressure. What that means mathematically is that pressure times volume is a constant. So as long as you are at constant temperature, then pressure times volume is equal to constant. In other words, if the pressure goes up, the volume will go down. If the pressure goes down, the volume will go up. If you have a closed system, you can describe this as P1V1 equals P2V2. So you'll have condition 1, condition 2. The only thing that's important about this is that it has to be at a constant temperature. So if it's not at constant temperature, you can't use Boyle's law. So let's look at an example of Boyle's law. And you can tell this is an example of Boyle's law. But, well, first, I suppose right up here at the top it says Boyle's law example. But let's say that wasn't there. Let's say that it didn't say that. Well, you could tell that this would be a Boyle's law example because the temperature is constant. You'll see the temperature is 23 degrees and it's still 23 degrees at the end. So that tells us that Boyle's law is probably the right law to use. All right, a volume of CO2 equal to 20 liters was collected at 23 degrees Celsius and 1 atmosphere. What would be the volume of CO2 if it were collected at 23 degrees Celsius and 0.830 atmospheres? All right, so just like when we're doing any problem, the first thing you want to do is determine what are we looking for. And here we're looking for volume, and we're going to say it's volume 2 that we're looking for. So we need P1, V1, and P2. Well, the quantities that we have there are V1 is the volume, the 20 liters. P1 is the pressure 1, so 1 atmosphere. And P2, which is the 0.830 atmospheres. Clearly, the temperature is constant, which validates that we can use Boyle's law. All right, so the pressures, and if you put the units in, then you can do dimensional analysis to make sure that everything cancels out properly. All right, and we end up getting a value of 24.1 liters. So not too bad, not too bad. Okay, so next we want to look at Charles' law. So Charles, he was across the English Channel in France, and you'll see that it's about a century later. And you can see he looks kind of like a French aristocrat there. Anyway, that is Charles, and Charles came up with this formulation, which is the volume occupied by any sample of gas at a constant pressure is directly proportional to the absolute temperature in Kelvin. And I don't know that he said it in Kelvin, but he did say that it's directly proportional to the absolute temperature. And of course, he said it all in French because, you know, he was French. But what that means mathematically is this. Volume is equal to a constant times the temperature. If you double the temperature, you'll double the volume. Now, we're not particularly concerned with what that constant is because that constant will depend on what pressure we're at and how much gas we have. So we're not particularly interested in that constant, although we can solve for that constant. And when we do, we get the constant is equal to volume over the temperature. Another thing that we can say about this is that if we have a closed system, we could have, volume over the temperature equals a constant, and then some other volume over a different temperature would equal the same constant as long as it was at constant pressure. So we would get this formulation, which would be V1 over T1 equals V2 over T2. And that is Charles' law. All right, so let me show you an example of Charles' law. If we expect a reaction to produce 4.38 decimeters cubed, a decimeter cubed, by the way, that's just a liter. So 4.38 decimeters cubed of oxygen gas at 19 degrees Celsius and 101 kPa, what would be the volume at 25 degrees Celsius and 101 kPa? Well, here again, we're looking for volume 2. We know that it's okay to use Charles' law, not just because it says Charles' law at the top, but more importantly, it's at constant pressure. So it is at constant pressure. So we get V1 over T1 equals V2 over T2. We're looking for V2. All right, we're looking for V2. So when we solve that for V2, we get V1 T2 over T1, and we put the numbers in. So V1 was the 4.38. T1 is 19 degrees Celsius, but we need to convert that into Kelvin. So we'll add that to 273 to get it to Kelvin. And T2 is 25 degrees Celsius. Again, we'll add that to 273, and we'll get our value in Kelvin. And now we just put those numbers into our equation, and 4.38 times the 298 over 292 will cancel out our kelvins there, and we will get this, that volume 2 is equal to 4.47 decimeters cubed. Okay, so now we are going to switch over here. Make sure I've got everything in view of the camera. Okay, so a fixed quantity of gas at 23 degrees Celsius exhibits a pressure of 735 torr and occupies a volume of 5.22 liters. Use Boyle's law to calculate the volume the gas will occupy if the pressure is increased to 1.88 atmospheres while the temperature is held constant. Again, temperature is constant. That's what tells us that this is a Boyle's law. And Boyle's law, of course, is P1 V1 equals P2 V2. And we're looking for volume 2. So volume 2 is equal to P1 V1 over P2. All right, and now we just need to put the numbers in. So V2, P1 comes from up here at 735 torr. All right, V1 is 5.22 liters. Okay, and P2 is 1.88 atmospheres. Now, one thing that we want to do is we need to convert because we have torr in atmospheres here and they don't cancel out. So we'll put 1 atmosphere is 760 torr. So 760 torr. And now we're ready to do our problem. So 735 times 5.22 we'll divide by 1.88, and then I'm going to hit enter and then divide by 760. Divide by 760. And we get, let's see, 3 sig figs here, so we're going to say 2.69. So 2.69, I put that point in there. And that is the volume, and the volume should be in liters. Let's go ahead and look at our dimensional analysis real quick. Atmospheres cancels out, and torr cancels out. All right, and temperature was constant, so that's why we were able to use the Boyle's law. Oh, we do need to put the units there, liters. So 2.69 liters. Not very beautifully written there, but that's okay. All right, now this one says use Charles' law to calculate the volume the gas will occupy if the temperature is increased to 165 while the pressure is held constant. So this is going to be V1 over T1 is equal to V2 over T2. And we're looking for V2, and again, pressure is held constant here. That tells us that we can use Charles' law. So V2 is equal to V1 T2 over T1. Okay, so next we want to put the numbers in. V1 was 5.22 liters. So V2 is equal to 5.22 liters. T2 is 165, and we'll need to get that in Kelvin. So 165 plus 273, and that gives us 438. So 438 Kelvin. And then T1 was our initial temperature of 23, so 23 plus 273, and that gave us 296. All right, and our Kelvin cancels out, and that's going to give us our answer in liters. So we'll clear all that out. We'll get 5.22 times 438, and then divide by 296. And that gives us 7.72. We only have 3 sig figs, so 7.72 liters. All right, so that is our Boyle's law and Charles' law. Boyle's law and Charles' law. So, but before I show you the combined gas law, I'm going to flip back over here. All right. So I've written down Boyle's law. Boyle's law is at constant temperature, P1V1 equals P2V2. I encourage you to write this down and just kind of memorize this. And Charles' law is at constant pressure, so V1 over T1 equals V2 over T2. And so we can use that. Well, there's another one that's who was a contemporary of Charles, and his name was Gay-Lussac, also French. So the Gay-Lussac's law is at constant volume, and it's the other factor that we haven't had constant yet. So P1 over T1 equals P2 over T2, as long as it's at constant volume. Well, we can combine all of these together to get something that we call the combined gas law. So our combined gas law tells us this, that P1V1 over T1 is equal to P2V2 over T2. And the great thing about the combined gas law is that if you know what's constant for these other 3 laws, you just cover that up and it'll show you what that law is. So for example, Boyle's law is at constant temperature. Well, if you cover up the temperature, look, you've got P1V1 equals P2V2. If you've got Charles' law, which is at constant pressure, if you just cover up the pressure, well, my fingers are a little bit fat there, V1 over T1 equals V2 over T2. And similarly, the Gay-Lussac law, if we just cover up those volumes, we'll get P1 over T1 equals P2 over T2. So the combined gas law is really, really handy because it takes everything into consideration, and you don't have to hold any of those things constant. You can vary all of them. So let's go back over here to the in-class, or not the in-class, but the presentation, and we'll see that with Boyle, P1V1 equals P2V2, here's Charles, and we can combine those together to give us P1V1 over T1 equals P2V2 over T2. All right, well, here is a combined gas law. Nothing is constant in this case, except for the amount of gas that we have. A balloon contains 5.41 decimeters cubed of helium at 24 degrees Celsius and 101.5 kilopascals. Suppose the gas in the balloon is heated to 35 degrees Celsius. If the helium pressure is now 102.8 kilopascals, what is the volume? This looks like a complicated problem because there's a lot of variables, but that's okay. It's not too terribly difficult. We'll just solve this equation for V2. All right, and we'll put in each of the values. So V1 is the 4.51 decimeters cubed. Here is T1, 24. Of course, we're going to add that to 273 to give us 297 Kelvin. 101.5 kilopascals. So there is our P1. And then here is T2. All right, at 35, again, we're going to add that to 273 to give us 308 Kelvin. And then finally here is pressure 2 at 102.8 kilopascals. If we take those numbers and put them into this formula, all right, so here I've solved this for V2. I multiply both sides by T2 and divide both sides by P2. We'll get V2. And I kind of cleaned it up here to make it look all pretty. All right, we put the numbers in. Our units, kilopascal. Ooh, I've got different colors. Our kilopascals and Kelvin cancels out. And we end up getting 5.54 decimeters cubed. All right. I do not have an in-class assignment problem for the combined gas law. But you know what? I forgive myself for that. Yeah, you'll have plenty of practice on the homework. All right, we're going to get another law, and this is Avogadro's law. And yes, it is the same Avogadro. And here is what Avogadro's law tells us. Equal volumes of any two gases at the same temperature and pressure contain the same number of molecules. Now, another way of saying this is that the molar volume of a gas at a given temperature and pressure is a specific constant independent of the nature of that gas. So here is what we mean. All right. So here I've got three gases. I've got, let's see, helium, and we've got 22.4 liters of it. It's at 1 atmosphere. It's 0 degrees Celsius, and it's going to contain exactly 1 mole of helium atoms. All right, here we've got 22.4 liters, 1 atmosphere, 0 degrees Celsius of nitrogen, and it contains exactly 1 mole of that gas. Same thing here with methane. It contains exactly 1 mole. What that means is that the volume of a gas is independent of the size of the gas. All that's really important is how many moles of gas do you have. So let's look at, and here is our molar volume. Molar volume at STP, and STP is these conditions. Pressure is 1 atmosphere, temperature is 0 degrees Celsius. Now, this is not to be confused with standard conditions, which we will see in chapter 5. When we do that one a little bit later. Standard conditions is 1 atmosphere and 25 degrees Celsius. This is 1 atmosphere and 0 degrees Celsius. It's convenient to make it 0 degrees Celsius because ice was readily available at the time that scientists in Europe were coming up with this formulation. All right, so STP is 1 atmosphere and 0 degrees Celsius. So our volume comes out to 22.41 liters per mole. All right, let's look at number 28 on the in-class assignment. All right, so what are the conditions that are represented by the abbreviation STP? All right, well, STP means standard temperature and pressure, and I'll write that down. So standard temperature and pressure. Oop, too many S's there. Pressure. And our temperature is equal to 0 degrees Celsius, and the pressure is equal to 1 atmosphere. All right. What is the molar volume of an ideal gas at STP? And our molar volume is, that molar volume I showed you on the previous page is 22.41 liters per mole. Okay. Now, room temperature is often assumed to be 25 degrees Celsius. Calculate the molar volume of an ideal gas at room temperature and 1 atmosphere. So if we think about what it is that we're holding constant, we're holding the pressure constant. And since we're holding the pressure constant, that means that we can use Charles' law. So Charles' law, again, is V1 over T1 is equal to V2 over T2. And we're looking for V2. V2 is equal to V1 T2 over T1. V1 is this volume, 22.4. I'm going to just put 22.4 liters because of sig figs. So 22.4 liters. T2 is 25 degrees Celsius. And as you'll see, 25 plus 273 comes out to 298. So 298 Kelvin. And then T1 was the STP temperature, which is 0 degrees Celsius. That is 273 Kelvin. So that's 273 Kelvin. Okay. So now we'll punch those numbers in. 22.4 times 298 and divide by 273. And that gives us 24.45. We're going to call that 24.5 liters. All right, so 24.5 liters. So if STP had been defined as 25 degrees Celsius instead of 0 degrees Celsius, we would have had a larger standard volume there. Okay. So we're going to go back over here to our in-class, our presentation. And we'll do the ideal gas law. So the ideal gas law takes all of these things and blends them all together. So from Boyle's law, we get this. Volume is inversely proportional to the pressure. All right. From Charles' law, we get that the volume is directly proportional to the temperature. From Avogadro's law, we get that the volume is directly proportional to the number of moles. And if we combine these, we'll say that the volume is directly proportional to the number of moles times the temperature over the pressure. We just need a constant of proportionality to make this an equation. Well, that constant of proportionality is going to be the constant R. And it turns out that constant is a real constant. And in fact, that's one that we've got officially defined in our like on our periodic table. So when we rearrange this, we'll get the more familiar form of this, which is PV equals nRT. And PV equals nRT, that is our ideal gas law. And we just need to look at what is R, like what is this R thing that we're talking about. So what is R? Well, R is the molar gas constant, and it is the value that makes that equation true. Okay, without getting too elaborate, it's the value that makes this equation true. So the value will depend on what the units are. And so we've got different units that we use for pressure and volume and number of moles. We always have number of moles. And temperature, temperature we usually use Kelvin here. But the pressure and volume, sometimes those units change, and so we'll have different values. And so here is a list of values. Now, one of the values that we have is, 8.314 joules per mole Kelvin. We're going to use that actually quite extensively later when we do chapter 5 and a whole lot when we get to chapter 19. And if you're thinking chapter 19, yes, that's in the second semester. 8.314, if you want that in terms of a pressure and a volume there. Our pressure in pascals, the volume cubic meters per moles Kelvin, and that also is SI units, so that is useful. Here, this is one that we use quite a bit, 0.082057 liter atmospheres per mole Kelvin. I often will just round that to 0.0821 because 3 sig figs is often enough, but we have those values in case we need them. And let's see. Also, we've got, what is our other value here? All right, 62.36. This one is not used very often. Liter torr per mole Kelvin. You will see that it's a metric variant. All right, another metric variant, if you, instead of joules is a unit of energy. Instead of joules, if you use calories, you get 1.987. What I always liked about using this one, and it's hardly ever used anymore, but what I liked about this one is that that value is so close to 2 that you can kind of use 2 as a first approximation and get pretty close to your answer. And then this one, this is a U.S. customary unit, and we will not be using this in the class, but it is kind of funny. PSI, so 10.73 PSI, so pounds per square inch, foot cubed, foot or pound mole, and then Rankine to the -1. And Rankine is, anyway, this is a really weird unit. Okay, so if we go back up here, this 8.314, it's actually 8.314462618155324 exactly. And the reason is that R is equal to the Boltzmann constant times Avogadro's number. And in May of 2019, the Boltzmann constant and Avogadro's number were both defined as constant values. So now R technically is a constant value. Just for your reference, we're gonna go back over here to look at this, some fundamental constants that are for your use. So here, 0.082057366 liter atmospheres per mole Kelvin. Again, I usually just round that to 0.0821. And then here are some of the digits, 8.31446. I didn't put them all in there, but there is our gas constant. And so those are available for you when you take your test. All right, so let's look at a gas law example. According to your calculations, a reaction should yield 5.67 grams of oxygen, and it's O2. We do need to pay attention to what gas it is, what the formula of the gas is. What do you expect the volume to be at 23 degrees Celsius and 0.985 atmospheres? So here is our equation, PV equals nRT. We are looking for volume, so we need to get the pressure. We have the pressure right here. We're looking for volume. We need the number of moles, and we don't have the number of moles, but we do have the grams, and we know how to get from mass to moles, molar mass. So we can get from mass to moles using the molar mass of O2. R is a constant, and then T is our temperature, and we'll need to convert that into Kelvin to make this work. So there's our pressure. There's our temperature at 296. Again, we added to 273. Here, I just rounded the value of R to 3 significant figures. That should be fine. Here's N. N is 5.67 grams of O2. We'll divide by 32.00 grams per mole and get 0.177 moles. We'll carry that value over and put it in here. So 0.177 moles. Here's the 298. So there's the temperature. Pressure is down here at 0.985. And then R, I just moved off to the side. And if you move it off to the side like this, then it makes it easy to do the dimensional analysis. So our moles cancel out, Kelvin cancels out, atmospheres cancels out, and leaves us with liters. And our liters here comes out to 4.37 liters. All right, so we want to look at numbers 32 and 36. Okay, so here is 32. Get the calculator lined up there. So 32, we've got 4 problems. They're all going to use our ideal gas law, PV equals nRT. And you'll see what makes A, B, C, and D different is that it's what unit is being asked for. So the first one that's being asked for is the volume. So let's go ahead and do that one. So volume is equal to nRT over the pressure. All right. N, in this case, we've got 1.75. There's the pressure. There's the temperature. So 1.75 moles. All right. I'm going to move R off to the side here. Our pressure is 0.985 atmospheres. And, I goofed up. I wanted temperature there. This is why I always write down the units. It's because if I don't, I make mistakes. So it is a teachable moment here. All right, so -6 plus 273 gives us 267 Kelvin. And then pressure is 0.985 atmospheres. And then here our value for R is 0.0821 liter atmospheres per mole Kelvin. And then if we check out the units and see what cancels out, we'll see that moles cancels out, Kelvin cancels out, atmospheres cancels out, and that's going to leave us with liters. All right, so 1.75 times 267 times 0.0821 and then divide by 0.985. And we get 38.9. That sounds good. So 38.9. And you'll see the only unit left there is liters. And of course, it was asking for the volume in liters. All right, I'm just checking with my key that I have made, make sure I didn't goof up anything. And it's good there. All right, so next we're looking for the temperature. So we're going to solve this equation here for temperature. And it is absolute temperature, so it'll be PV over NR. So PV over NR. Our pressure is 725 torr. All right, volume is so 255 milliliters. Since we're going to be using the liter atmosphere, so let's go ahead and convert that to liters because that's easy to do without a calculator. So 0.255 liters. N is the 3.33 times 10. I got a little carried away with the 10 there. Let's try that again. Times 10 to the -3 moles. And then R is in the denominator, so I'm going to write it like this. 0.0821 liter atmospheres per mole Kelvin. All right, and then we need to do one additional little conversion here, and that is our torr and atmospheres. So we'll put 1 atmosphere is equal to 760 torr. All right, we're definitely going to check our units here to make sure everything cancels out. So torr cancels out, atmospheres cancels out, liters cancels out, and moles cancels out. And that's going to leave us with our answer in Kelvin. So that will leave us with our answer in Kelvin. And so now we have to actually calculate that. All right, 725 times 0.255. All right, divided by 3.33 times 10. all right, times 10 to the negative 3. I like to get the calculator on screen so you guys can see what I'm pushing. All right, so that's that part. We need to divide by 0.0821, and then we also need to divide by 760. So divide by 760. And we get 889.7677. We've got 3 sig figs here, so we're going to call that 890. So we're going to call that 800. I'm going to write down the whole number, 889.77 Kelvin. But now we're going to round that to 890 Kelvin. We do have 3 sig figs there. All right, so now let's look at pressure. So we're going to solve this one for pressure. So up here we're solving for P. So P is equal to nRT over the volume. The number of moles is given there at 0.0467 moles. And then R is 0.0821 liter atmospheres per mole Kelvin. And then temperature is 122. We'll do 122 plus 273, and that gives us 395 Kelvin. And then our volume, I'm just going to put it down here in the denominator. It's 413 milliliters. We're just going to write that as liters, 0.413 liters. All right, and let's just make sure all our units cancel out to give us our units of atmospheres. So moles cancels out, liters cancels out, and Kelvin cancels out, and that's going to leave us with atmospheres. So let's clear all that. We'll do 0.0467 times 0.0821 times 395. And then we'll divide that by 0.413, and that gives us 3.6669, and we have 3 sig figs, so we're going to call that 3.67. So 3.67, and our units of pressure here are atmospheres. So 3.67 ATM. Okay, so next, let's look at the quantity of gas in moles if 67.5 liters at 54 degrees Celsius has a pressure of this. So we're looking for our quantity in moles, so we're looking for N. We solve the equation for N. N is equal to PV over RT. So our pressure here is 11.25 kPa, and we'll do the conversion here in a minute. Our volume is already in liters, so that's convenient. So 67.5 liters. And then temperature is 54, so we'll do 54 plus 273, and that gives us 327 Kelvin. And then R is also in the denominator, so I'm going to put 0.0821 liter atmospheres, and then mole Kelvin up there. And then we need one additional conversion here, and that conversion is between atmospheres and kilopascal. 1 atmosphere is equal to 101.325 kPa. Right, because it was 101,325 pascals. So 101.325 kPa, that will work. And now let's do our dimensional analysis. So kPa cancels out, atmospheres cancels out, liters cancels out, and Kelvin cancels out. And of course, that's going to leave us with our answer in moles. So we'll clear all that. We've got 11.25 times 67.5. All right, divided by 327, and I might enter, divided by 0.0821, enter, and then we're going to divide by 101.325, and that gives us 0.279. We had 3 sig figs with the volume, so we're going to go 0.279, so 0.279, and the answer is going to be moles. So 0.279 moles is going to be our answer there. All right, we want to look at number 36. And after number 36, we'll stop this video and we'll do the next video on, we'll do the next section starting the next video. All right, so if the pressure exerted by ozone in the stratosphere is 3.0 times 10 to the negative 3, and the temperature is 200 Kelvin, how many ozone molecules are in a liter? So first, what we're looking for is we're looking for the number of ozone molecules. If we can solve, so here, PV equals nRT. If we can solve that for n, then we can use Avogadro's number to give us the number of molecules. So we know that we can do that because we just did that on that problem before. PV over RT is equal to n. And now we just need to put in the values here. Our pressure is 3.0 times 10 to the negative 3 atm. Our volume, this is kind of tricky. Our volume is hidden here in the word a liter. So we're just going to we're going to assume it's exactly 1 liter, and it'll have as many sig figs as the other thing, so 1.0 liters. Our temperature is 250 Kelvin, and then R is 0.0821 liter atmospheres per mole Kelvin. So let's check our units. Atmospheres cancels out, Kelvin cancels out, liters cancels out. That's going to leave us with moles. All right. So we'll clear all that, and we'll get 3.0 times 10 to the negative 3. All right. Times 1. I'm not going to multiply times 1. And then divide by 250. And then we'll divide by 0.0821. And that gives us this. And I'm going to go ahead and write the extra sig fig there because of some weirdness. So I'm going to put 1.46 times 10 to the negative 4 moles of ozone. And then we'll round in the next part of the calculation. So we'll take that 1.46 times 10 to the negative 4 moles. Okay, and that's moles of ozone. I'm going to go ahead and write that out. And then for every mole of ozone, there are 6.022 times 10 to the 23rd ozone molecules. And you'll see that the moles of ozone cancels out. So I'm just going to leave that number in the calculator and multiply by 6.022 times 10 to the 23rd. And that gives us, and we're going to go ahead and round to 2 sig figs here because we're done with our calculation. But 8.8 times 10 to the 19 ozone molecules. All right. Well, that is the end of that section. I'm going to double check there. Yeah, that's the end of that section. And so we'll start up with section 10.5 in the next video.